how do we go from this to this? To help us with that, we turn to Dr. Cindy Chestek.
So is the question like getting primarily the augmentation of getting past human capabilities?
That is the question. Cindy is the Associate Chair for Research in Biomedical Engineering and an Associate Professor at the University of Michigan. She has earned those titles by publishing a massive amount of research focused on signal processing and prosthetic devices, while also working directly with prosthetic manufacturers, giving her a complete sense of what we can and can't do in the prosthetics world.
Okay, so you're asking us what we can't do, right?
So Michael and I will then drill down with her to figure out exactly why her lab is able to get signals from nerves orders of magnitude higher than some of their competing labs. Keep listening to hear our full discussion with Cindy, and be sure to like, subscribe, and all of those things for various recommendation algorithms. And get ready for another episode of Sci-Fi to Reality. Hi, Cindy. Welcome to the show.
Sure. Thanks for having me.
All right. So, as we understand it, your lab specializes in doing kind of signal processing of muscles and being able to then map those over to prosthetics or other external devices. Could you tell us from like a pretty abstract, high level, how those work and what your lab does differently compared to other people that are sticking nails in nerves, so to speak?
Okay. Yeah. Okay. So you specifically want to talk about nerves, or do you want to talk about nerves and brain? So, because my lab does the whole range.
So I do want to get into brains, but let's focus from a prosthetics perspective for starters, and nerves specifically as they pertain to muscles, and then we'll tend toward brains eventually here.
Okay. Cool. Yeah. So my lab works on trying to get nerve signals to a form that we can actually use them to control a prosthetic hand. And the reason that we don't have that so far is because, there's just all kinds of physics problems with trying to record a measurable signal directly from a nerve, right? So if you try to put like a cuff around the nerve, you get an incredibly small signal, right? You're talking about a very, very well insulated wire, right? And so you get, microvolts of signal if you try to put something around a nerve. And if you start stuffing things into the nerve, the nerve scars, and, you can only do that for so long, and you get this very impermanent interface, right? So, very smart people have been trying to get signals from nerves for decades now. And this is really, really hard to do. So what my lab does is we work with this wonderful team in plastic surgery that invented a new surgery that actually takes a cut nerve and turns it into a muscle. So they take a small piece of muscle graft from the same person, and they wrap this very, very thin piece of muscle around the end of the amputated nerve. And it's so thin that, it doesn't need blood vessels right away. It can sort of survive. There's no other nerve innervating that piece of muscle. So there's nothing for the nerve to compete with as it grows in. And so the nerve grows into that thin piece of muscle that's surrounding it. And we call this a regenerative peripheral nerve interface because of that nerve regenerating into that very small piece of muscle. And then it's an honest to goodness muscle. Like, you can actually see it contract under ultrasound when somebody tries, moving their thumb. One of the coolest things we saw was somebody who had a very high level amputation. So like no finger muscles remaining. And we asked him to move his thumb, and you can just see this muscle contracting. And so there's a thumb muscle in his tricep. And whenever you see it contract, you're going to have a really big EMG signal. So from my perspective, I just want the voltage to be big. A contracting muscle has a much bigger voltage signal than putting a cuff around a nerve or something like that. So then, my group comes in, and, we've, at this point, we implant indwelling wires, and that's also the plastic surgery team. That's Dr. Cederna. And then my group takes those signals, and we run it through our machine learning algorithms. And I'd like to think our machine learning is pretty good, but it's just the signals are much bigger now, right? Like, and you can see, like, if your eye can detect like which of these different movements you want, between like thumb, pinch, point, things like that, then almost any classifier is going to do pretty well with that.
Wow, that's awesome. So yeah, that kind of answered my next question. The next thing I was curious about was I've seen that you guys get a couple orders of magnitude larger signals than a lot of the historical work, and I was going to try and delve into why, but you answered that for me, which is awesome. Um, so okay, so that's the abstract view on the muscle grafts there on nerves, and then if we go the opposite direction, then if we go all the way up to the brain, then what is the work on signal processing in the brain? Because presumably you can't stick a muscle graft inside somebody's head, or
Yeah.
into their brain tissue
So
if you're trying to do it.
Yeah, so let's talk a little bit about the physical difference between recording from cell bodies and recording from axons, which is the part that like sort of sticks off the cell body. So neurons have like this big giant cell body called the soma, right? And then it sends
Mm-hmm.
off like a wire, which is the axon. And if you have a nerve, you're talking about axons, right? So axons, very, very hard to record from, right? Like you can kind of do it in very special cases, right? Extremely small electrodes, very controlled laboratory environments. Like it's not impossible to record from that axon. But near that cell body, there is a giant current source and sink, right at where the axon starts. So like the link between the cell body and where the axon starts, there's a huge number of like sodium potassium channels, right? So big current in, big current out, right there, right? So this is a long way of saying that in the brain, I actually have the cell bodies, right? And so it's much easier, and it's always been much easier to record a signal from the brain than it is to record a signal from the nerve, right? So, in the 90s, people developed some pretty great electrodes for, putting, like the Utah array has 100 electrodes. If you put it in the brain, you're going to get pretty decent signals, right? Maybe they don't last for 10 years. Maybe we'd like them to be bigger, but you get a really nice selection of neurons. And so, people have been learning how to interpret those neuron signals for a long time. And it's actually been really interesting doing the brain and the nerve, because now that the nerve signals are big, all of these machine learning approaches that we've developed for brain signals, we can now turn around and use those for nerve signals because they're now big, if that makes sense.
It makes a ton of sense. So I want to turn this back towards prosthetics in a moment,
Yeah.
but in BCIs and brain computer interfaces, oftentimes you have the problem of there's a lot of neurons, and to be able to actually, as I understand it anyway, and so to be able to accurately read and get any accurate information from this, it's like trying to read off of the individual transistors off of a computer. They're so densely packed. Trying to get your uh, get your monitor on any individual piece of the chip and actually know what it's doing seems like a very hard problem to me. So could you expand
Yeah.
a little bit on how you actually are able to get usable data that's from individual neurons in the brain?
Yeah. Okay. So the problem, I would say, of too many neurons is not a common one, right? Like we all want more signals,
Okay.
right? So like I think
Okay.
yes,
Fair
there's all
enough.
these like big, new electrode arrays that record more neurons. We have not yet had too many neurons, and we'll let them know when we have too many. Like right now, we want more. People are really trying to push
Sure.
on trying to get to 1,000 channels instead of 100. Even when you put 100 electrodes in the brain, maybe you only get like 30 really good neurons. And so actually probably all of the videos you've ever seen have been with like, the dozen good neurons that, you get after the end of that whole process, right? So we absolutely need more
Okay.
neurons. On the other hand, I hear what you're saying, because it is kind of like the perfect machine learning problem, right? If you sort of stare at all of these sort of neurons going past as they're firing, right? The pattern is in there, but it's super subtle, right? And so, this isn't so much like, I would argue, a neuroscience problem, though, obviously neuroscience can help us. It's a machine learning problem. Like the relationship is not obvious. And so, we use algorithms that have been developed for other things to try to pull information out of those neurons. Right. And so, I'm happy to talk about how that's done. But, I think the more the better in terms of input, because it is a machine learning problem.
Sure, that makes sense. You have tons of data points, so being able to actually figure out how to make sense of that high dimensional data is use machine learning. Sure.
Yeah. There's a lot of cool techniques for
So
trying to make sense of high dimensional data. And so, we use some of those, but some of them are sort of for visualization, for trying to understand what's going on with the neurons. But then there's actually like
mhm.
decoders, right? Which is like, okay, I'm trying to interpret and turn this into a movement command right now, right?
Sure. All right, so let's take a step back for a second, and then let's drift towards prosthetics. So you have these pretty high potential signals that you're getting, and you're feeding them through some machine learning algorithm. Presumably, the machine learning algorithm then is saying, okay, that one is associated with moving the thumb, and now we move the thumb on the prosthetic. So what are the limitations there, I guess, on going from on building a prosthetic now that has the same ability as I have with my hands now, so to speak? What are the biggest things holding you guys back from making something like really incredible
Okay, so
or
you're asking
as
us
good as
what we
human?
can't do, right?
Yeah.
Yeah. So I mean, I think that so one thing, is um, we are now very limited by the prosthetic hand. So we work with some truly state of the art prostheses. They're very cool. We work with the Deca hand. We work with the 5-fingered Oser hand. They are absolutely state of the art. Um, However, none of them, so first of all, none of them are sort of, have control schemes that assume that you have big nerve signals, right? So for example, the movements are sort of linked. They're sort of set up in modes, where, you assume that you can't do all these things at the same time. So you're switching between them. The Decahand has these 3 fingers locked. So they're very cool, but we end up doing a lot of our experiments in animation, because so if I want to show that I have like good ulnar nerve control over movements that we can't do, we have to do that in animation, right? So the hands are absolutely a limiting factor. Um, that said, just to be sort of more fair to the technique, we are kind of limited in channel count, right? And that's based on how we implant the wires. So right now we're doing everything we're doing between 8 to 12 wires, right? And it's hard to find a medical device that can even handle that many channels in an implantable system. So we are pretty limited by the channel count, and we are always sort of uh, thinking about our channel budget. Like, do we want another thumb electrode, or do we want another wrist electrode? Like, this whole thing would be a lot easier if we just had 100 electrodes somehow.
So that makes me want to ask the question: if somebody showed up with a prosthetic arm that could take 1,000 different signals, would you guys actually be able to leverage that? Like, how far could you hypothetically go with your tag?
Yeah. Well, I mean, okay. So let's take a step back, and I don't want to like overclaim. The
Sure.
things that we've sort of shown so far, right, is we get, for example, pretty good control over 2 degrees of freedom of the thumb at the same time, right? We have pretty good control over index and middle ring small at the same time. When we start trying to do all of these things together, we can make publication videos, but we start to have a significant number of errors, right? Wrist signals. We haven't had a hand with a prosthetic wrist so far, but so I can't comment as much. But that's about the level at which I think we can get pretty good control over the prosthetic hand.
Really cool. I've been stealing all the questions here, Michael. Do you have any thoughts, or
Yeah.
maybe we
So
could?
Yep. So you're talking about how you're pretty limited by the prosthetics themselves. Are you guys working with the makers of the prosthetics on the mechanical side or mechanical or electrical
Yeah,
side
we
to
are. And
get
they've been
these
great,
higher
but
capabilities?
yeah, they've been great, but we just keep asking. So what we want is sort of completely unlocked access to every degree of freedom. Yeah, particularly we're really grateful to OSER in particular. They really came out and helped us. We had our study participant cannot lift the decahand. Right, it's very heavy, so they're helping us out. They gave us a smaller hand. It's the smallest one that's sort of available clinically, and so for a very petite woman, we needed that super small hand. But yeah, no, their engineers have been great, but we just keep asking. We want
Okay.
access to all of the individual fingers. They're working on it, and they're definitely working with us. We want access to the wrist at the same time. But they've been great, and we're absolutely talking to prosthetic hand manufacturers. We're talking to a few of them also.
Okay. So, I mean, building on that, I don't know how much you know on this subject since you're mostly in the signal processing world, I guess. But are you aware of what the other limitations, what the physical side limitations are on the prosthetics, like
A little bit.
power wise
I
or
can comment
other
on that.
stuff
I
like that?
mean, there's sort of this unfortunate relationship between weight and power, right?
Right.
Where I mean, like the decahand is super cool. I don't know if you've ever seen it move. It's very
Right.
fast. It's very strong. You can do all kinds of things with it, but all of that is at the cost of being heavy, right? And that's sort of the major limiting factor on using it. The lighter hands are weaker, right? And so they're still functional, they're still useful, but I know that the prosthetic hand manufacturers are constantly fighting against the weight. And also, battery lifetime is an issue, and the more battery power you're carrying around, the heavier the whole limb is. And I mean, if you guys, if you
That
think
makes
about
sense.
wearing, a 2 pound weight on your hand all day, right? Like it would be very, very difficult. And
Yeah, it's
people,
not
this is why
trivial.
prosthetic hand abandonment is so common, unfortunately.
Wow. Yeah, that's a shame. Especially since, to my knowledge, prosthetic arms are really expensive, right? So I could imagine somebody getting a really expensive arm and then they just can't physically pick it up, so they have to stop using it.
Yeah, well, I mean, they would obviously be that would be a communication with their prosthetist, and a process of trying to figure out what
Okay,
works for
sure.
them. But yeah, but it is fairly common
Okay.
to get a prosthetic
So,
hand and have it not live up to their expectations and have them, stop wearing it. So, and that's what we're
so at
hoping
the
to get
risk
around.
of
So,
continuing to drill down, gotcha. At the risk of continuing to drill down into this area, if is that weight mostly in the actuators, or would that be like battery power? So I'm trying to like understand what's like the first principle limiter. Is it like energy density storage in the batteries, or is it that the motors are physically heavy? Like could you?
I think the
I'll
hands. So
leave it at that.
we're getting well out of my area of expertise. I'm an electrical engineer, but
Sure,
the
sure.
motors are in the hand, right? So it's definitely the motors that are
Gotcha.
heavy in
Yeah.
the hand, and the batteries are in the socket. And I mean, with the battery power, it's hard to run a prosthetic hand for more than 4 straight hours, right? In these sort of
Right.
intensive things that we do where we're just constantly having them do stuff with the hand, it can, run out during the course of our experiments. So,
Makes sense. All right, so I think we've gotten fairly far here without making any mention of science fiction at all. And the underlying goal of our podcast in theory is about trying to connect research with science fiction. So we've kind of touched on these topics, but we haven't like really delved into um, the idea that we wanted to hit from a sci-fi perspective, and that was kind of well, in a lot of science fiction, you see people walking around with prosthetics that are better than organic limbs, right? And so, what we kind of wanted to start to work with you on and imagine with is, and we've started to get into what the existing limitations are, but I'd be curious to hear your perspective on what do you think it would take, and if you had to make a wild guess, how long you think it would take to get to a point where you could have a prosthetic limb that could beat out a human limb, if at all possible.
Yeah, I mean, well, I'm glad everybody agrees that the future should have nerve-controlled prosthetic hands, right? That this should be something that, like,
Right.
you can go to the doctor and have this treatment available, and everybody who loses a hand gets it. I'm glad we all agree on that. Okay, so is the question like getting primarily the augmentation of getting past human capabilities, or is it, yeah, is it
That
that?
that's the dream, right? Is to be
Okay.
able to get to the point. And,
Do I
and of
think
course,
it's
that's kind
possible?
of
Do I think it's
where our
ethical?
show gets kind of.
So, okay. Yeah, I mean,
Well,
so
let's hit both, but one at a time.
yeah, so I mean, okay, is it possible? Absolutely, right? In terms of and also like, there's we talk about all the time. There's no reason that you have to use these EMG signals to control a hand, right? Like in a sense, we spend a lot of time trying to figure out how to get a prosthetic hand to type on the keyboard when we can achieve that with Bluetooth, right? Like we can decode the signals, we can figure out which fingers is moving, and that's going to be a much easier lift than trying to redo the hand and redo the hand to keyboard interaction, right? So that's one thing that need not be true, right? And some of the prosthetic hand maker community is really amazing in terms of the things that they have hooked up to somebody's prosthetic hand. Um, on the topic of, and yes, you can make a prosthetic hand that's stronger than a hand. The DECA hand has all kinds of safety constraints in it, right? And it has a very, very firm handshake, right? So, yes, you could absolutely build a hand. It would be heavy, that is stronger than a normal hand. And also, I do think that neuroprostheses broadly, like imagine a far far future where it's very safe for some reason to get at these signals. Yes, you could imagine a future where you use it to control like an exoskeleton or something that is stronger than a person. So there's certainly no rules about how you use the signals. um, but in terms of like, is that going to happen soon? No, absolutely not. This requires a surgery, right? Now, and when you're talking about someone with
Yeah.
an amputation, they're already having surgeries, they're already having treatment. The way that we do it, there's also another like added health benefit that it tends to help with phantom limb pain and neuroma pain. So there's reasons to do that surgery. I don't think anytime in the near future you're ever going to see surgeries being done on an able-bodied person. And just by physics, you're not going to get signals like this from the non-invasive interfaces. Like, at some level, you can't fight the physics.
Makes sense. Um, and then I think maybe you had covered this, but you also had mentioned that you saw potential ethical concerns there too. Could you expand on that? And if I'm misremembering,
Oh,
you
well,
can
no, I mean,
let
I
us.
think that, it is, so first of all, let me say that I am so incredibly grateful to our study participants who volunteer to have a surgery that they didn't need to have in order for the potential that it helps somebody else, right? Like this is sort of to develop the future system that is going to help future people with amputations, right? So they are heroes, they are pioneers. And so and I am very grateful for all of the ethical regulations that go into those interactions. We have a tremendous oversight both at the university and through the FDA. And this whole process of taking an invasive technique all the way out to clinical use is something where you have to pay attention to ethics at every step of the process. You have to pay attention to the consenting process, and you have to make sure that people always understand that the risks that they're taking. And so super grateful to all of our all of our prosthetic user volunteers.
It's really great to hear somebody in research that's doing the hard science be really gung ho about all the ethical stuff, because a lot, like, I'm a software engineer, right? So oftentimes when I'm going through cycles and regulation, I'm like, it works. I know it works. I've tested it, and so it's good to hear somebody that is working with other people who is heads down in the science is also excited about and glad for the regulation
Yeah.
associated with it. So that's cool. Cool to hear.
Yeah, and I'll just add to that. It's really sort of easy, like for us. So my team, we're the engineers. We're very obsessed with bits and volts, right? Like how much information can we get through? How big can we get the signals? it's been really educational for us to actually start working with people, using the prosthetic hands. And we're trying to make this into like, okay, but can you use a coffee maker better? Right? Like those are the sort of questions that we have to take those bits and bolts and turn it into useful functions. And that is a whole, you just realize that it's more like you're at the starting line than you're at the finish line if you can see the signals. So and I've been doing that a lot in collaboration with a lab in kinesiology run by Deanna Gates. And so, we're evaluating, okay, what does this actually mean? Like say, yeah, I can generate control signals for 4 different grafts. So does that make it easier to make coffee? Right? And it's actually not an obvious question. So
Yeah.
So building on that, what do you see as actually the next steps in your signal processing and control schemes
yeah.
for
Yeah.
prosthetics?
So for the prosthetic specifically, I think we're at the point where we know enough about how, like, what signals we need, and where we can sort of start to make an improvement in that coffee task, among other things, that we need to make the system fully implantable. Right. So right now, our participants have a connector on their arm, and it's very tiny wires going through the skin. But I don't know if you've ever seen like these diabetes implant patches. It's very similar to those, right? So they're wearing that, and they can only ever use it when they're hooked up to a cart. Right. So, one of the most sort of like forward looking thing we're doing, I think, is making all of this portable. Like at this point, I think we can sort of, we can lock down like a first set of algorithms that work. We know what the signal processing chain should look like. And so we're working with an outside company to try to make everything fit into a small implant that, so our person can actually walk away from the cart. And so people can actually use the system at home. So that's the immediate next step.
All right, sorry, I'm gonna ask for a clarification here because I might have missed that. When you're saying walking away from the cart, that's like a cart that is physically connected to the patient that they have to be connected to for your signal processing. So that's moving to
Yeah.
like a wireless setup.
Yeah, so let me take you through what one of these experiments looks like, right? So our participants have like a patch on their arm, and there's a little connector there. So they come into the lab, and we it's always covered with gauze, so we'll attach to the connector. That signal runs into a FDA cleared human bioamplifier, right? That is, where the electrical safety is well paid attention to. And then those signals feed into a computer. That computer runs our algorithms. And then that goes to an extra circuit board that then drives the CAN bus to the prosthetic hand. So, in our videos, you mostly see the person and the hand. But, there is a whole cart of computers that are actually sort of generating that. But luckily, nothing we're doing on those computers, couldn't fit inside of an implantable device.
Very cool. So to change tack for a second, something that I'd be very curious to know is there is a lot of sensationalism in tech journalism and research journalism in general. And I'd be very curious to know if there's anything that bothers you that journalists have a tendency to get wrong about your work, or like work that is close to yours or tangential to yours, that if you could take a moment to set the record straight,
Yeah.
if
So
there's any items in that wheelhouse.
Yeah, I mean, I think that like so my experience with science journalism has been very positive. I think that your average article about a scientific study is sort of excited about it, sort of talking about the future, and so. But I think among that enthusiasm, that you can often oversell, and that's why I try to be really careful when I'm talking about it, and like there's sort of the language we speak to other scientists, which is very, very precise. And it's very sort of easy to, say something or imply something, when you're talking to a journalist. And then so oftentimes you sort of see on the other side, it's one step too optimistic. Right. And so when I read these articles, I have to say sometimes I feel bad for the scientists because I'll read something in the article that there's no way the scientist said that. Like it's, like they know, everybody knows you can't do that, right? And so like, I can't imagine for a second they said it, right? But it can sort of, it made its way into the article. It was slightly oversimplified, et cetera. So like, I think that, you know, it is hard to get an idea of how well something actually works without, reading the scientific publication, which has like all of the actual numbers in it. Or for example, seeing the video, right? Like, I think that you get a pretty good idea of how something is working by watching like a video of how well it works, right? In a way that, you can't get from a news article about, how well something is working. So yeah, so I mean, I think that I think science journalists try really hard to get it right, and like I really enjoy talking to science journalists usually, but usually those conversations are like, okay, but like this is cool, it's an absolute advance, but like no, you can't, do all these things that that you're hoping. It's not quite there yet, right? And so yeah, but
Yeah,
overall, yeah, very positive.
Yeah, so that's
that's
why we
great.
like to go straight to the scientists if we can for this podcast to see what you guys are actually telling us. And so we have a primary source there. And in order to not oversell these prosthetic limbs you're working with, I
Yes.
want to check. So these limbs you're talking about, these are taking signals for movement of the limb,
Mhm.
but they aren't returning any feeling, are they? Or are
Yeah,
they?
no, I mean, I would say, well, okay, so this is it's a good question. So yes, we absolutely do sensory stimulation, right? We inject current and we ask the
Okay.
person where they can feel it, and it's usually a referred sensation to the part of the hand that makes sense. So if we stimulate near the ulnar nerve, they're going to feel it like in this part of their hand, like near the pinky and ring finger. But the limitations of the approach is that we are not able to make that feel like a natural thing. It always feels like a weird electrical buzzing. So it's in the right spot, but like, it doesn't feel like somebody's touching your hand. Um, and I would say other techniques are better for that, right? So going into the nerve, cuffing the nerve. There's some great work going on at both Utah and Case Western, where at least in some cases they're able to get something one step more natural. So nobody yet can make it feel like your hand, like reliably every time. But both of those groups have like clear examples of times when it was working really well, right? And it felt like somebody was, just feeling a touch on their hand, and they're a little bit closer to the nerve, and that means you can stimulate at lower currents. So, I think that, for us, we are not in the nerve. We are slightly distant from the nerve, and that's a good thing from the perspective of nerve health. But if you're trying to do a sensory stimulation, it's better to be in or on the nerve.
So you mentioned that there's some other groups there that are focused on it, perhaps on getting realistic sensations more than you. So I don't want to push you out of your wheelhouse too far here, but um, with that in mind, could you expand a little bit on what? So we have the muscle graft around the nerve, as I understand it,
Yeah.
and so that's the extra distance you're talking about, and right?
Yes.
Is that correct? And
Exactly.
then
So our
for
electrodes
those,
inside the muscle, not like on the nerve. So, but they're a
yeah.
few millimeters away
So
from the
if you
nerve. Nerve
then
fibers.
So for these other options that are stimulating the nerve directly, you have another approach where you have the electrode directly inside of the nerve. And is there, you said cuffing a nerve? Could you expand on what that is?
Yeah. Okay. So there's a couple of ways to interact directly with the nerve. So most actual clinical applications, if you're going to have something directly interact with the nerve, it's more often a cuff, which means that it's a little like clamshell that closes around the nerve, and that's a little bit less invasive than sticking something inside of the nerve. And you can use that cuff to stimulate. Unfortunately, it's really hard to record from a cuff, but much easier to stimulate. And you can put multiple contacts on the cuff, so I can stimulate on one side of the nerve or the other side of the nerve. You can steer it a little bit, and this is work primarily being done at Case Western, for example. Um, So, so that's one way of interacting with the nerve. There's the other thing you can do is you can put the electrode into the nerve. So, for example, at Utah, they take it's a tiny bed of nails, and they will push that bed of nails into the nerve. And they actually the electrodes are different lengths, so they go into different distances and hopefully stimulate different parts of the nerve. And there's other groups doing this at, Florida International University and at University of Texas. And so, and they're sort of, some cases they're sort of going sideways into the nerve. Sometimes they're going through the nerve. But all of these techniques, require having something penetrate the nerve. So, it's a little more invasive. It's going to generate a little bit more scar tissue, but they have been able to show that they can use this to get useful prosthetic sensations.
Okay, and this is me digging through stuff that I don't know that well about. So pardon me if I put my foot in my mouth here, but I have a memory of invasive procedures like that. Some of that scar tissue that you were talking about there, that can cause permanent damage to the nerve, where you have to then progressively go further up the nerve as the nerve treats, potentially if it's at the end of the nerve that you're.
So yeah, that's true. So scar tissue is a bad thing, right? You would not do
Yep.
this to a perfectly healthy nerve, right? That it was not a treatment for something worse, right? So again, if you're talking about an amputation, there you do this in a nerve that is not going anywhere, right? I think if anything, I think we've been surprised how stable some of these interfaces are. Like, which is to say that, like, there's been a flurry of recent work in humans. And yes, they're like, I'm sure those electrodes have scars, right? Like they are absolutely scarred in there. But it's more or less working over time, right? Like I think it's, like in the sort of, at least the single digit years kind of thing, you can continue to stimulate on these electrodes for a long time. And similarly, like most of the clinical treatments that we have that involve neural interfaces, they're stimulation applications. Like it's much easier to stimulate than record. Right. So, because you just, if you get a little bit of scar tissue, you turn up your current a little bit. Right. And so, and as long as you don't have to turn it up to dangerous levels, it's still going to work. Right. Deep brain stimulation. Like there's absolutely scarring along those electrodes. So, the current has to be high enough to deal with that. Right. But then it works.
Okay, and so your techniques with the muscle graft around the nerve. So as far as you've seen, that also lasts for a pretty long time, or have you had
Yeah.
any
Yeah.
issues?
No, that's lasting a very long time. So let me, talk about the difference between like, so recording is hard from a axon or a soma, because if the electrode gets pushed by 100 microns, you're in trouble. Like your signal is gone. Um, if you stick an electrode in a, let's say, a heart, right? So you want to make an automatic defibrillator. That's a big, healthy muscle signal, right? And it scars in, but you're going to still be able to see that big, healthy muscle signal for decades, right? So recording EMG is just much easier, right? It's a much bigger signal, and you can record it through the scar. So I'm quite sure that our electrodes have a little bit of scarring around them, like any other electrode, but it's an EMG electrode. Like it's very similar to a cardiac electrode. And so, yeah, it's recording from EMG for decades is a solved problem, right? Signals are big, it'll work.
Okay, that's good to hear. Um, Changing tack a little bit, you mentioned that you've done some work on brain machine interfaces as well. I think we touched on it
Yeah,
earlier, but could you? I didn't read much of your work in that area compared to the prosthetics.
that's
Could
okay.
you expand on what what your lab is doing in that area?
Sure. Yeah. So I mean, it's not at all unrelated to the human work. We've actually it's just been a real privilege to get to take some of our animal work like all the way out, like from animal work to human work. But we started that work in animals also. But my lab focuses entirely on multi-degree of freedom finger movements, right? So people have previously used brain machine interfaces for simpler movements, for cursor control, for things like that. And we're trying to get very precise control over individual fingers. So, for example, We're about to publish a paper on showing that we can control index finger and middle ring small finger precisely at the same time. So, brain signals alone, we can record from motor cortex, and our animals can, acquire two targets at the same time to get apple juice, and then they can do that, with brain activity. So that's we're trying to get to these multi degree of freedom movements, because if you're going to get a brain surgery to restore hand movements, you're probably going to need more than just a simple open close.
Sure. So,
And there, I would say also our goal is to eventually also link this to stimulation of a paralyzed hand. So, we're thinking about this in the case of spinal cord injury specifically.
okay, so if somebody has a vertebrae damage so they can't feel the left half of their body, you'd be able to still control prosthesis. There's no nerve connection there,
That's
so
the
to
plan.
speak.
Yep. Or to
Okay,
to record in the brain and stimulate in the paralyzed arm.
sure. So, um, there's been lots of hype recently in brain computer interfaces, and do you think you would eventually get to a point where you could have a brain computer interface where it would be, because you could watch the motor cortex directly? Do you think that would end up eventually being better than trying to monitor, for instance, your nerves in your arm or something like that, for doing stimulation of the entire prosthetic arm?
Okay,
If that
so
makes
you're
sense.
asking specifically about using brain in the case of amputation.
Yes.
Yeah. Okay, so I will say, right now we see no reason to do that, right? We can get very good signals without doing a brain surgery. And, a brain surgery can be very safe, but it is no joke, right? And so an arm surgery is safer. And so there's absolutely no plans, right? Like no group that I am aware of is working on brain implants for controlling a prosthetic hand in the case of amputation. So not happening right now, right? To my knowledge.
Sure.
Um, that said, yes, you can imagine a future, forever is a long time. And there's an awful lot of real estate in the brain, right, for getting a lot of signals. So, it is absolutely true. I think if, imagine, lots of time passes, we have a way of putting 1,000 electrodes safely all over motor cortex. It's been established technology for spinal cord injury for, decades. Yes, I think that ultimately, the physics of brain recording is more favorable than the physics of nerve recording, even when you're reconstructing it. So, in the limit of, if I have to get a 10,000 channels from somewhere, I think physically you have to go to the brain for that. Right. So, eventually, but like maybe not in my life.
Sure. Sure. That makes sense. Oh man. All right. And okay. Okay, I'm gonna change tack a little bit. Is there any, to go back towards our science fiction topic a little bit?
Sure.
Is there any idea in science fiction that has particularly inspired you, either in your work or just in general in your life, or are you like heads down and just excited about what the next step in the application can be, etc.?
Yeah. Well, so I mean, first of all, I'm a huge science fiction fan, right? So I read a lot. It's a lot of fun. I think the most fun brain machine interface book that I've read is Lock In. Right. It was super fun. I
Hmm.
got to go to a conference once and, sit next to John Scalzi and, talk about the science side versus the science fiction side. And it was, it's fun. Like it's again, the science fiction is obviously way beyond like what we're actually doing, right? Like I like to say, okay, the world record for brain machine interfaces is something like 10 bits per second, right? And that's amazing if you're controlling a computer cursor. Like a computer mouse is, much like, it's not very many bits per second. So if you're a person that needs that control signal, it's amazing, but it's not exactly the matrix, right? Like, there is no way of making that sort of high bandwidth interface, right? That's sort of in the science fiction. And so, it's going to be a very, very long time before we have anything like the sort of, assumed technology of the future for BMIs. Um, That said, I can make an argument that brain machine interfaces are sort of at the beginning, right? In terms of all of the things that we could do better. And it's because, like I said, every video you've ever seen is what we can do with relatively simple algorithms and about a dozen neurons, right? And so, it's really easy to imagine what we could do if we had 1,000. And it's also like, we don't need fundamentally new things to achieve that, right? And I think that that's sort of like, for example, there's a lot of demos of using subcellular electrodes. So electrodes that are smaller than neurons, right? And those are actually still pretty big compared to computer traces and things like that, right? Like, we have nanometer wires. Like, if we just could like Star Trek warp it into the brain, there's a lot of room in there for the wires. And very small wires don't trigger the immune system to the same extent as like the much larger wires you're using. So what's exciting to me and why I could never leave this field is you can sort of see all these parts that could come together. They all have practical problems, right? Like, there's so much engineering research that has to be done to like put all of these different pieces together. But you can imagine a future where we are wirelessly recording from 1,000 neurons, right? And those electrodes are so tiny that they're not causing a big immune response, right? So it can be done safely. And and you can imagine that all happening within 50 years, right? Because we're already sort of seeing the beginnings of each of that in the research. And honestly, like this whole field barely existed 20 years ago, right? Like, some of the first super compelling demos, which were done in monkeys, were 2002, right? So this is like, if you fast forward by 50 years, you could end up taking this technology really far.
All right, so I have to ask then, once again, at the risk of getting too excited about technology, have
Yep.
you seen any of the Neuralink stuff? And also, there's a company out in Europe that I'm blanking on the name of that also is there that is doing those really small wires that you were describing, directly inserted into the brain to, in theory, pick up thousands of neurons, or then through a machine learning algorithm. And we have working demos and monkeys and pigs and I think the company in Europe just got human trials approved for the end of this year, I think.
What specific company are
Do
you
you
talking
have?
about in Europe? Or I'm just curious.
I do not remember it off the top of my head. I can spend a couple minutes Google
Yeah,
searching, but
I'm very familiar. Yeah,
I
I'm familiar with a lot of these companies. So,
sure.
but I wasn't. Yeah. So yeah. Yes, they are absolutely working on this, and I think it's based on sort of the putting two and two together that I just described, right? So, and I am super like. I don't think they're wrong. Like, it might be too early. There might be practical problems, right? Like, it might be sort of 5 or 10 years before it's time, but like, it might not be. And it is sort of time to sort of put a professional engineering team behind the ideas that we know are already pretty good, right? And so yeah, so I'm really excited. I mean, I think we sort of watch the demos now. Like, on the other hand, I don't want to get too excited. The demos have not yet sort of surpassed stuff that's already happened. Like, it's getting I'm really glad that some of this stuff is sort of making its way to the popular, like, videos. um but like, it's we haven't seen anything to say that there's something fundamentally new at these companies, right? And so, and I think, but it's also very easy to see that happening in the next 5 years, should some of these approaches work, right? So,
Yeah, that makes sense. Yeah, I remembered seeing the Neuralink demo and kind of thinking, well, if you're monitoring the motor cortex in the monkey playing Pong, you should be able to do what it's doing of moving its arms up and down and getting the thing to go
Yeah,
up and down
so let's
fairly
I
simply,
can give an
right?
example. So the Pong video, I mean, it's very good, and I should say that, like, the engineers at Neuralink are great. They've recruited all kinds of awesome people, like, out of academia, and so they it's state of the art. They know what they're doing, but that's a 1 degree of freedom task. Like, the reason it looked amazing is because they
Yeah.
were only controlling 1 degree of freedom, and that's good enough, right? And the
Yeah.
2 degree of freedom control was good. It was absolutely good, right? But probably not the best video I've ever seen, but like it was very good. And if they actually get all 1,000 channels sort of, working and everything, working together. And I'm sure they have a massive sort of systems level problem on their hands trying to get every piece of this to work at the same time. It should look better than that with 1,000 channels. And I'm sure the Neuralink engineers would agree with me.
For sure. Cool. Really, really fun to kind of get your take on the Neuralink stuff and all that whole world.
Sure.
Let's see, Michael. Do you have any other thoughts? I'm still looking for the other companies I was thinking about too.
Yeah. Are you talking about Paradromics? Like they're another, because they're also in the
I
US.
really don't know their name. I just remembered seeing
There's a
some of
company in
the headlines and scrolling through a couple articles.
Yeah, the company in Australia is a different one. So are you talking the stentrode, the one that goes into blood vessels?
I did read about the stentrodes, and I thought that was really interesting, is because that looks less invasive potentially, and like you would be able to potentially monitor the whole brain, which would be crazy. Maybe eventually
Sure.
in some far off future. Yeah.
It's a cool idea. Yeah.
Yeah. So I think, sorry, Michael, you didn't get a chance to follow up on me. Any other questions coming to mind here before we start to think about wrapping up?
I think we can keep going through our wrap up questions here. Well, not wrap
Sure.
up, but our last few. So your work is really fascinating, right? Just want to tell you that working on these brain machine interfaces and the signal processing with prosthetic limbs and all that is really great. And so if there's someone out there watching this show who would be interested in getting into that field, what would you recommend they do? How should they go about learning about these things and getting a career doing
Yeah.
this?
I mean, I would say, okay, I would definitely advise them to become an engineer, right? Like if you're talking about, like the fields that are sort of, contributing to the technology development. But there's a lot of ways of doing it, right? So like I would say, so my background is in electrical engineering, and there's obviously a big part of this that is like signal processing, machine learning, and circuits. That said, I'm currently in biomedical engineering, and the things that we do that are fundamentally biomedical are trying to make these electrodes safer, right? So things like our subcellular electrodes are very much on the biocompatibility. So biomedical engineering is a really good choice for that. An unexpected, I would say, dark horse major is if you are an expert in making materials last forever in harsh environments. I actually think that is the sort of big group of people that we're missing. That's our actual biggest problem. Right? The brain is a very harsh environment that attacks our electrodes, and making them smaller didn't necessarily make that better. So that's something where I think we need more people from that field. Certainly mechanical engineering, like, I work with mechanical engineers in my lab, and, we need better prosthetic hands. We need better controllers for electrical stimulation. So, I would say stick with the math, right? Like, it's pretty competitive, and so keep taking the math. Make sure you take linear algebra and stats as an undergrad. Any of those majors worked. But that's the advice I would give.
So I
And
wanted
if you
to
don't mind sharing,
go for it, Michael.
okay, yeah. If you don't mind sharing, what was your path to getting into this?
Yeah. So, okay. So I actually, let's see. So I was a physics major. I realized I wasn't going to solve the mysteries of the universe, so I became an electrical engineer. And then I was sort of advised to go try to find like, some kind of research job for the summer. And I couldn't find one in electrical engineering. So I wandered over to the biology department, where it was a sea slug neuroscience lab. So Dr. Hillel Cheel took me in for a summer. And as soon as I started, recording from live neurons, like I knew I could never do anything else for the rest of my life. Like that was the coolest thing ever, right? And it actually turns out they love electrical engineers in neuroscience labs, right? Like it's just one never-ending circuits problem. So then I was, so I spent a lot of time doing neuroscience work, and then I ended up in brain-machine interfaces because it's like if you take the average of electrical engineering and neuroscience, that's sort of what you end up with. So I decided to go to grad school. I got my PhD in electrical engineering, got to work with Krishna Shenoy, who is just wonderful as a PhD advisor out at Stanford. And I think I sort of stayed and became a professor because I think you reach a point at the end of your PhD where, it never gets easy. You're always working on stuff that's mostly failure, but once you reach a point where you just can't leave, right? Like there's no way you could go work on something less interesting after having worked on brain machine interfaces. That's when you become a professor. And so that's when I became a professor. And, I've been very, very happy with that decision.
Sounds like a blast.
Sure.
So
you were going to say something before I asked my question, Doug.
I was. I don't remember. Let's. So one of the last things we always try to ask here is what would you like to promote? What, be it an idea, a book, a movie that you would like to have people go check out, a research paper or another researcher, or just something that you really enjoy. What's something that you would like other people to go look at and check out?
Okay, sorry. I need to think about that for 2 seconds here.
Yeah, for sure. No worries.
Yeah. So first of all, for a science fiction recommendation, everybody should read The Three Body Problem. So if you haven't already, that's an amazing book. It has totally changed my worldview. I've been really enjoying the science fiction over the pandemic. Okay, so I mean, I think in terms of I don't know, like technologies. So so what's going wrong is like my brain wants like 10 different things. And you just asked me to like, either pick my favorite kid or pick my favorite, mentor or
you can list them out. That's totally fine with us.
Yeah, give me a topic. So cool electrodes that are out there. So for example, other sort of I'm obviously excited about our electrodes, which are very small. I'm also excited about Changji's electrodes, right? So that's at that's at Rice, and so those are also very small, very flexible. I'm excited about some of the precursor technology to paradromics that's using that's at Stanford with Nick Malash, and they're sort of using a military camera to attach very small electrodes. So that's super cool. In terms of like, okay, so the algorithms, like I would say work that we sort of follow very carefully. Miriam Shineki at University of Southern California. That's sort of, I think, a really innovative approach to the algorithms that are, they're one step more complicated than what we use. So we're definitely looking into that. And then also in terms of like the human work. So the coolest demo, right? Like the coolest thing that's happened so far, I think, is brain controlled stimulation of a paralyzed limb at, the C4 level. So this was done at Case Western by Balu Ajiboye. And so, if our research is going to sort of help something along, we'd really want to support brain machine interface for functional electrical stimulation. So that is something that I think is very exciting.
Could you expand on what the C4 level is?
Oh, so this was somebody that, couldn't even lift their arm versus gravity. And why I was so excited about this study is it's the first time so I'm offending lots of people by saying this, but it's the first time like you see an actual like clinical improvement, right? Like he was eating mashed potatoes and like, it was only a couple degrees of freedom at the same time. But eating mashed potatoes, drinking coffee, and it was his own arm. Like we've seen this with robots before, but honestly, I think our goal is going to be to restore function of the body. Right. And so, yeah, I think that that's sort of the most exciting thing that has happened in the past 5 years.
That's really, really cool. And then, at the risk of rat holing, can I ask, at a super abstract high level, how they managed to give him his arms back, even if only by a few extra degrees of freedom?
Yeah, sorry, that is what I think is so exciting. I think it is the first time. So there's also another excellent study that was done at OSU, but the brain controlled functional electrical stimulation studies is the first time like a physical therapist would walk in and say, yes, this person has more function now. Like you have successfully treated their condition at least a little bit. And so that's why I'm so excited about it.
Gotcha. But when you say they treated their condition, how did you actually go from somebody that couldn't physically lift their arms to somebody that could lift their arms? Like, did you amplify the signals? Or
let me explain. So this is also, unfortunately, only when they're hooked up to the cart, right? So
Sure.
Utah arrays in the brain, so tiny bed of needles, embedded in motor cortex. Connector comes off, goes to the cart. Algorithms interpret, try to figure out what movements are intended, goes to another box that generates stimulation current. Those go into wires that are going through, one of those connectors I said on the arm. And that was making the hand move, the elbow move, and the wrist move, right? So again, it's not something you could take home, but it's something that, it was actually seeing somebody do something that they couldn't do before.
That's fantastic. That's really cool. Well, thank you so much. Your excitement is infectious and makes me want to go study neuroscience. So I really appreciate you for coming on the show. It's been a ton of fun talking to you.
All right. Thank you so much for having me. This was a lot of fun.
And that's a wrap. So thank you so much for listening to this episode of Sci-Fi to Reality. We hope you enjoyed it. We also hope that you go check out our website, www.scifi2reality.com. That's www.scifiToreality.com. You can also go check out our Facebook page, Twitter, Instagram, the whole gambit. And you can also find this podcast wherever you personally get your podcasts, along with our YouTube page. I hope that you guys enjoyed it. Give it a share, comment, like, subscribe, all that good stuff for the various recommendation algorithms. We really appreciate it. Thank you so much for listening, and we'll see you in the next one.